Okay, let's start. This is our first class in parallel programming, so let's introduce yourself and myself. Okay, let's start with getting to know each other. My name is Alexei Doludенко. Name Alexei, surname Doludенко. Of course, I'm from Russia. Do you know Russian? Maybe a little bit or no? A little bit, no. But without any terminology, just okay, just in room you can. Yes. Okay. Let's start our class. So. We will study, you will study parallel programming or how to write your own parallel programs and to launch it on the supercomputers. That's all. I will speak about something, you will listen, and from time to time, you will do your homework. Homework will consist of several tasks. We will study different technologies of parallel computing. And I think it will depend on your understanding on how you will be. Will you be good in solving your tasks or not? So I will see that, and I will give you more or less tasks. We'll see. But firstly, we will start with MPI. Message parsing interface. After that, I suppose we'll speak about difference. I suppose one simple task. Here will be two tasks and open MP. So, this is our plan on this semester. These tasks are not so complex, and you can write it, you can do it yourself by yourself, and there are sufficient time to do this. So, this is just up to you to find time and to write by yourself. The main goal is to write these programs by yourself. Let it be not so good, maybe a little bit worse or bad. The main goal, you have to do this by yourself. Okay? Okay. Are there any questions about tasks and about what I have said?
So this semester will be only having tasks, nothing else?
No. Why? No. We will discuss. I will speak about something, about how to do this task, about all of you. You can ask. We will discuss and so on.
No, I have an exam in the end.
And then, I don't know. As I understand, there's no any explanation there.
Quiz.
So,
Quiz?
Quiz. this course is more for practice. Okay, of course, there will be some theoretical part, but mainly you have to do it by yourself, so to make practice. Any questions?
Is there any possibility that we're going to use CUDA?
Please a little bit louder. Possibility of what?
CUDA. If there is any possibility that we're going to use CUDA.
CUDA? No, our course does not contain CUDA. CUDA is, I think, it should be additional course. It's rather deep learning, I suppose, more complex than this one, a little bit. So we will not discuss about CUDA. So, okay, let's go further. What about high performance machines and so on? Why is it possible to study these machines and how to operate with them now? Because firstly, when all computers were created, almost all of them were parallel machines, but they were specific ones and just specialists who deal with them. There are not so many specialists that worked at these machines. The situation had changed. The situation had changed when you can see new processors had appeared. Approximately in the late of 18th. Firstly, they were rather cheap, economical, and effective. Firstly, they were cheap. These new machines, and people there was possibility to combine these cheap machines in one big machine, and it was named as a cluster. Cluster system. Because this machine was rather cheap, that means that more and more people can work with this machine. More machines, parallel machines, more people. And these people which can work on this machine were not specialists in this domain. They just were programmers. Not programmers of parallel programs, but just serial programs. Ordinary serial programs. And there was a question: how to learn a lot of people, not specialists in parallel programming, to program or to deal with this parallel machine cluster? One question, yes. Okay, just make the point at this table. How to learn? Or how to. Okay.
But what's the difference between parallel?
Yes. Yes, of course. So the main the main issue is: should we make new program language to use this programs on these clusters or not? And the answer was, okay, there are a lot of people that knew, for example, C or Fortran languages. So it's not a language. Maybe it will be complex, I don't know. So why not use learning of these languages, C or Fortran, and to add something? Some functionality in these languages. To use functionality of parallel machine, something like this. Okay, this is what about this issue. And another question is Moore's law was ceased to operate. So people encounter it with the physical border to make processor faster and faster. So we can say that now frequency of processors is about 5 no hertz. Yes, of course. And this limit was achieved approximately 15 or 20 years ago. So what to do further? Further, we can combine these processors into one piece, and it will be another approach to make parallel machine. So this approach was not new, because these machines with combining of different processors were earlier. But now it was, how to say, naturally to make performance higher and higher, because Moore's law ceased. Okay? Do you know about Moore's law? Yes? Do you hear? Did you hear? Huh? Maybe in school?
No, something like that. I heard of it, but not.
Okay, it was about every processor double its performance. Every 2 years, for example, firstly years, the performance of new processors twice. So performance will be twice. And it was exponential growth of performance during time from 16 to till beginning of our century. So it's like this, something like this. Time, performance, the performance grow, but let it be like this. This growth starts to be slower, and slow, like something like this. Or another way to say about Moore's law is every 2 years, the number of transistors in each processor was twice. Okay, double of processors every 2 years. But now there is a physical limit of thermal conductivity of processors, and
there is a limit in temperature, something like this, in temperature, and limit now in the size of each transistor, because they how they made light, so like photography. It was called as lithography, I suppose. And the size of the smallest transistor is limited by the length of light. And now we can, I think, say about 4 micrometer of size technology, yes. And for example, length of light will be approximately, or maybe less, okay, less than 1 micrometer. They're comparable. Okay, maybe we make transistor even less than this one. For example, 1 micrometer or even half micrometer. But further, there is no any physical aspects to make this transistor less than this value, for example. So this is somehow physical limitation to achieve higher and higher performance in one core, in one processor. So we should or have to combine processors. One way to make clusters, another way to combine simple processors in one crystal, and so on. Okay, we will discuss about this technology and how to deal with this technology in a programming way a little bit later. So now this is just introduction, okay? You may know about this or maybe not, but okay, let's start with touching of some information about problem. Okay, what else? So there are no, okay, let's say four approaches to okay, not approaches, but a array of application of such high-performance systems. Firstly, time complexity calculations. For example, these calculations you can encounter with these calculations in science. Okay, because there are a lot of calculations in modeling some processes. For example, hydrodynamic or solid state systems or conductivity and so on. Especially when you consider 3D systems, 3D volume, and there are a lot of calculations, and so this time complexity. Okay, and we will deal with this area, time complexity. We will solve program to make time of calculation less than it was in serial code, for example. So our goal is to achieve some time which will be less than in serial. So this will be called as speed up. What does it mean? Time of working. Okay, let's suppose that we solve the same problem. We can solve this using serial code and parallel code. And we suppose if we make good parallel code, so it should run, consume less time, yes? That means that T1 time of serial code will be more or greater than time on several processes. Let it be P, a lot of processes. So time of parallel code and time of serial code. We suppose that it should be greater than 1 or even much greater than 1. This is our goal. You have to remember this statement because in your programs, in your task, when you will complete or will make your own task, you will calculate this speed up and draw graph of speed up on number of processes. So you have to learn and to remember this statement. It is very useful and simple. Okay, which other areas? For example, there are so-called spatial complexity. And so maybe you can hear this as a big data problem. Big data in Google, Yahoo, and so on. How to deal with big data of internet. So this is another application of high-performance machines. Another area is real-time tasks. For example, in industry plants, you have to make some decisions in real time, and high-performance machines will help you to do this. Another is when you have to make some high reliability, for example, in spacecraft or in aircraft, you have to use double system, for example, or high-performance double system. But we will speak about just first area when we deal with time complexity. A lot of calculation, and we want to make them, or not them, time of these calculations less. Okay, so let's go further about but about high-performance machines and of their classification. Okay. I have said about clusters, for example, and some machines based on some processor with several cores. Okay, let's speak about this in more detail, about these machines. So there are a lot of classifications. You can see Hockney, Fenk, Handler, and so on. But we will speak about Flynn's classification as more reasonable, I suppose. There are 4 English words to make this classification. Which one? Which they are? S is for single, yes. M is for multiple. I is for instruction, and D is for data. So, because every high-performing machine, or even, doesn't matter, high-performing machine or low-performing machine, this machine deals with some data, and you have to make some modification of this data, yes? Or maybe this data was created during its calculations, and so on. So data should be. Instructions means when you modify this data, you have to make instructions of processor, I mean, on this onto this data. Okay, so you can see that you can construct for classes using these 4 words: SI, SD, or SIST, shortly. This is ordinary serial machine with von Neumann architecture.
Why does it have 2 sets? S is for single. SISD has 2 sets. Single instruction for single data. Okay, that means you use one variable, for example, and you make one instruction with this one data, this one variable, like variable A, for example, and you can say A plus 1, for example. SIMD means single instruction for multiple data. A lot of data, A, B, C, D, and simultaneously there is one instruction lies onto all of this data. This is vector computers. It was more popular before clusters in 16th, 17th, and 18th, for example. Cray, did you hear Cray computer? It's rather, how to say, popular, not popular, but maybe you were hearing these American Cray computers. In Soviet Union there was BASM 6, big electronical machine number 6, also vector computer machine. It's our history a little bit. Okay, MISD, multiple instructions, single data. In reality, I think there are no any real machine, maybe in some laboratory, when you deal with if statement and prediction of branches in this if statement, something like this. But in reality, there are no any machines in these classes. And the class of our interest is MIMD. MIMD means multiple instructions for multiple data. This class is of our interest. MIMD. This class includes all types of parallel machines, contemporary parallel machines. Any questions? What is the parallel machine?
Which?
What is the parallel machine?
What is the parallel machine? For example, with this one.
How do you define it?
Define? Yeah. Firstly, of course, this machine has to contain a lot of processors or a lot of cores.
So any device which contains a lot of processors is called a parallel machine.
Yes. Because to make this time less, we have to somehow divide our task into parts, and each part have to be launched onto one, let's say, core. have to be calculating using just one core. And when you combine a lot of cores, that means then you can divide your program or your task into several parts, each part for one core, and so on. But as I have said, there are different ways to combine these cores. Different ways. For example, SIMD also somehow another way to make this time of calculation less. It's almost, we can consider these machines, vector machines, as parallel, but not so much. So one can consider these machines as parallel. Other people know. So it's under discussion. Just let's say this vector machine, but also they can give you time less than in serial code. But we will deal with MIMD machines, not vector. And in MIMD class, there are also some classification. Because clusters are here. Machines combining different cores on one crystal also here. Okay. Let's consider this class MIMD. You can see that roughly, can I say like this, roughly? Yeah. Maybe. So MIMD machines can be divided in two classes. First class is shared memory machine, and another class is distributed memory machine. So what about distributed memory machine? This is simple. All clusters are distributed memory machines. So MPP means massive parallel processing. This is the same as cluster. Rather cheap machine. Okay, we can consider this cluster as ordinary personal computers. Yes. Okay, we can consider this cluster as a lot of personal computers which are linked with some network. That's all. Shared memory a little bit more complex, let's say like this. They can be symmetric, you can see symmetric multiprocessing, uniform, or this is the same, uniform memory access. This is, okay, let's start from the very beginning. So what about shared memory? About distributed memory, are there any questions? You can consider as like personal computers are linked with some network, okay? But there is another class. Shared memory. What does it mean? Shared memory means that as I have said, on one crystal there are a lot of cores. For example, contemporary cell phones or notebooks, they are all shared memory machines because they contain, for example, 4 or 8 cores on one crystal, and they have these cores, different cores. They have just one shared memory. You can see, 1 minute. I even have laser pointer. and it works. That's good. So you can see different cores on one crystal, core 1, core 2, core 0, and so on. And you can see they are connected with just one shared memory. Yes? What does it mean? That means that during calculation or during solving some tasks, parallel tasks, they can read the same cell in the shared memory. There are some difficulties, maybe some issues, but nonetheless, they can read or write into one cell. This one can write here. This core can read from here, and so on. Some operating system and your applications, for example. This is uniform memory access. What does it mean? Because this connection is uniform or the same for each of the cores. Okay? There are another subclass of shared memory is non-uniform machine. Non-uniform. What does it mean? There is, for example, we can divide the number of cores in, for example, two parts. One part is linked with its memory. Another part is linked with its memory. So, a little bit, I think we can make picture like this. It will be even better. So consider this one part in detail. Memory, how it will be? Okay, it can be like this. Memory, and this memory is connected with 1, 2, 3, 4 cores. So you can see here just one core, and you here several cores. And we can see that they are all connected with some intermediate communicator. This one. And now we can divide or consider in detail this core. You can see just one, but here will be more. For example, 4, 5, 6, and 7. And all of them are connected with its memory. Here you can see the same picture as it was in here. So you can see that all these 4 cores are connected with this memory in a uniform way. And so we can say with this part. But they also connected with intermediate communicator, some communicator, or interconnect, high speed, and so on. You can say as you wish in terms of shared memory machine. But these cores can read memory 1 through intermediate communicator. But they will read some information from this memory rather faster than from this memory, because there is some intermediate step. Let it be T1, here will be T2, and we can say that T2 greater than T1. And here this non-uniformity. Here every core can read approximately with the same time, read or write T1. Okay. Each core can read information or write with the same, almost the same time. But to write or read from memory 1, it will be T2 greater than T1, a different time. This is what about non-uniform memory access. What does it mean? This mean. Okay. Do you have any questions? And what about CC NUMA, cache coherent non-uniform memory access? What does it mean? Every core or every single processor has its cache memory. Every time when processor deal with some data, it copies this data from memory to its cache memory and make some instructions with this cache memory. It gets new values, some values, and it copies back these values from its cache memory into operational memory. But when all of these cores deal with the same cell, for example, some cell in here, and all of them write some information in one cell, there will be some how to say, some issue, something. In general, the result of their work will not be good or will not be right, because of they do not know, every core do not know about other cores. What are they do another cores with this cell? For example, this core does not know about another core. What do they do? What are they doing with this cell? This is cache coherent problem, and you can solve this problem using hardware, and this machine is called cache coherent non-uniform memory access machine, and you can solve this problem using software. And from this point we can use, for example, uniform memory access or non-uniform memory access machines and solve this problem just using software approach. But so from point of view of programmer, these machines almost the same, if exclude this cache coherent problem. So from your point of view, okay, your point of view, these machines almost the same, but these classes are much more less costly than this one. And there is another limitation. All shared machines now is limited approximately 64 or now maybe even 128 cores, not more, because of these buses, for example,
on this bus. So this is the bottleneck of these machines. We can limit with some data buses. Here, 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 here. So now there is some limit in number of cores. But as you can, okay, one question. How do you think, how many cores now in contemporary high-performance machines, like in top 500? How many cores can be? How many? 1 million? This one? Another variant? Huh? No, not mobile. Mobile phone, okay, it's a little bit, we can consider it high-performance machine, of course. It's a pocket computer and so on, but I will speak about much more performance machines, big machines. Like your computer, it's small machine. There is no. Okay, you can consider or imagine big machine with a lot of calculational cores or processors. And what do you think? How many processors can be in big high-performance machine? This can be in shared memory machine. I have said that this is limitation, some limitation, okay? But we can consider distributed memory machine or clusters. And what do you think? How many processors can be in the cluster machine? More than this value? More cores? How much?
Multiplied by 10 to the power of 100.
10 in powers of something. Yeah. Let it be n. And okay, n. The same question. 5. Oh, 5. So it will be if n equals to 5. That means 12, for example, 0.8 times 10. So 12 millions cores. Do you all agree? Can be, but not. So maybe this is the highest value. In reality, the number of cores a little bit less, for example, 1 million. But 1 million, even 1 million, it's much greater than 100. And and this was achieved by using distributed memory machines. Not shared memory. Shared memory here. But for example, here, less, but let's see, let it be like this. This is clusters. Huh? Hi?
Is this the correct answer?
Almost correct. This value is a little bit more than in reality, but approximately yes. The main thing is that this n equals to, you said 5, okay, 4, let it be 4. Much greater. The number of processors in the cluster much more than in a shared memory machine. But we can say, in reality, clusters is a hybrid systems. These machines, now contemporary machines,
this distributed memory, some like clusters, and we can say that there is not different personal computers linked with the network, but some nodes linked with the network between each other. A node can consist of shared memory machine. So contemporary clusters is hybrid machines, but maybe it's up to you. Maybe we will write, write program using understanding of this hybrid system, and maybe we will use approach of distributed and shared memory at the same time. Maybe yes or maybe no. It's up to you. I don't know how you will be good or not in your tasks and so on. And this is cluster machine, massive parallel processor. Architecture consists of, as I have said, consists of nodes, or we can imagine as nodes equals to just simple personal computer, for example, and in brackets, contemporary personal computer is shared memory machine, because it contains, for example, 4 or 8 processors on one crystal and just one shared memory and so on. So node you can consider as a personal computer, and each this node or personal computer has its processor, which can be which can be combined from 4 cores, cache of processor, some bus, and memory, its own memory. Bus means data bus or instructional bus. Not on the wheels, but it's wires, a lot of wires. If there are some connectors in the processor, it has some connectors. And how this processor can read some information from memory? There is wires, connectors from processor and memory, also connectors. And this is lines, wires or lines, and from these lines you can read or write some information from the memory. And these wires, a lot of wires, for example, 128, 256, and so on. These wires called as a simple word bus. So bus, it's a lot of wires. So this were some words about classification of parallel computers, about classes. Classes in words of organization with instructions and data. And after this, we can consider some class and consider in more detail from the memory structure, operational memory, I mean. Not disk, but operational. We can divide this class of machines in two big branches, shared and distributed memory. Shared memory have some difficulties, and another difficult is that they cannot contain many processors. But the programming is rather simple, simpler than it was or that it is in the distributed memory machine. And distributed memory machine, or massively parallel processors machine, or clusters. They have such a structure, and the limitation almost infinity in terms of number of processors. But programming is rather complex. And why all of you here? All of you here? Why are you here? Okay, this is the question. What you're supposed to learn? How do you think? Which one? Which one? MPP, SMP, Number, which one? Okay, shared memory or distributed memory? That's all, just distributed memory. Huh? SMP? Okay, so other people keep silence. Okay, MPI is for distributed memory. P threads, POSIX threads, and mainly OpenMP is for shared memory. So you will study how to make programs which will run on distributed memory machines using MPI and on shared memory machine using pthreads or OpenMP. And for hybrid, let it be in brackets, hybrid, at these contemporary clusters. MPI plus OpenMP at the same time. Okay, do you have any questions now? From all clear for you now? Please a little bit louder and slower, okay? Language? C. Using C. And another question. Did you get your login and password to enter some computer, high performance computer? No? So you do not have any login? It's a pity. Okay, so how to to do your homework and to make familiar with some machines, distributed or shared memory and so on, and to make your own programs, you have to get, I don't know how, but I think you will be informed about your login and password to enter some machine. This machine is in our university here, but you can you can enter it not how it will be удаленно вылетело удаленно. So you can be at home, but on your yes, of course, remote. You can remotely get access into this machine, and you can write your own programs, and these programs will be on this machine. You can launch your programs on this machine, and you can see the results. Results, I mean results values and results time. Because main goal is to make this time less, but another goal, two goals, make this time less, and another goal to get right answer. So answer and time. Okay, I suppose that because another part of our class today, I was supposed to make some program by yourself, a simple first MPI program. But if you do not have any access to remote machines, so this is a difficulty, of course. Huh? I have already asked, but I don't know the answer. So you have not, and maybe a little bit later, I think, you will be given this information about login and password, and also me. I do not have any login information about this remote machine, but I have another possibility to show you something now. Yes, it's strange. It's not my username. Yes, I see. I think what do you mean? This is small. Small d. This one. Yeah. 2. Okay, maybe. Alexei. No, Alexei. No, it's not me.
So you can find it in the settings. In the settings, you find your username here. At A.
A, of course, yes. Okay, let's start. So we now we're starting with MPI practice. So let's remind that MPI is for cluster, is for distributed memory machines. Yes, MPI. So. These some rather interesting diagrams, but they are rather old 2007. This was some interview of programmers, parallel programmers in the United States 14 years ago, but I didn't find any visual information about which parallel libraries and which languages are used now mostly. So you can see here two diagrams. First diagrams says you about which language most used when you deal with parallel programming. You can see here C first one, C++, and Fortran. After that Java and others. I think now maybe Java a little bit greater, but the whole situation is I suppose the same approximately. And about parallel library, MPI, first one. You can't see my mouse. Okay. MPI, the C, C++, and Fortran. So we can deal with C or C++. It's up to you. And you can see here on the first place is MPI. After that, pthreads. After that, OpenMP. I think the situation now is approximately the same. So you can see that we will learn, okay, we will deal with C, the first place, and first three places we also will study. So what about message person interface? So MPI. MPI means message person interface. As I have said, then the first chip clusters appeared. There was one problem: how to learn programmers or how to learn people to make parallel programs using this rather cheap in comparison with earlier machines like Ray and so on. How to learn these people to make parallel programs. And this was the natural approach when you use learning not learning, you use knowledge of already learned languages like C, Fortran, and just add something which is for just parallel. Some functions, some functionality into these languages. And this functionality is in library. You can just link your environment with this library, and now you can use these library functions in your program. And for Fortran, this library uses its syntaxes for C, syntaxes for C, and so on. And this library was written rather fast, and you can see that first variant appeared in 1993, and as I remember, the second version was presented in I think 1998 and so on. And after that, even the third version was appeared, but you can write simple and effective parallel program using MPI using just 1.3 version, even this one. So you can see that this was written was written fast and was already effective even with the first version. The main structure of this, how to make parallel programs. We can the main reason, how the main approach. Okay, you have, for example, some parallel machine. It has several cores. Let it be like this. How to draw? Okay, let it be like this. One CPU. So the main reason, the main reason to make this time less is to run some code simultaneously. So if we run some code simultaneously, that means we can at the same time do something. Make instructions, for example. But in this case, if you have just one task, like this one big task, for example, big one. If you use just one CPU, it will be time T1. To make time of calculation less, you have to put or to divide your task in 3 parts, for example, and let these 3 parts run simultaneously, each part on its CPU. But if they run simultaneously, that means the instructions have to be independent. Some instructions. If there is any dependency, that means you cannot simply divide your task and run simultaneously. It's a problem. So, if you run simultaneously, your task parts of your task have to be independent. That means your task or your program has some property. This property is called internal parallelism. What does it mean? How do you think? Internal parallelism.
That can be done parallelly. Can be split into.
Yes, you're right. So this property shows, can we divide or split our task into several parts and run these parts simultaneously? If we can split our task, that it has internal parallelism and it's okay. If we cannot, or another way, if task does not contain or has not internal parallelism, that means we cannot split this task into several parts. If we can, that means we can use several CPUs like this, and on each CPU will run one process. Do you know what does it mean, process? Do you know? Process, okay. it's a running application, simply. So process here, and process here. Every process will do something with your will do something with data, or will do something inside your part of task part. When processes finish their calculations with data, they can, they just finish their work, and that's all. And here, when they work simultaneously, you have to achieve speed up. So once more, process is a running application, or in other words, computer program that has been executed. Running application. This is process. If you run your task using MPI, that means some of your task will be executed by one process, another task by another process, third task part of your task with third process, and so on and so on. And the main goal is to make this part of processes work simultaneously. Okay?
How many clusters does MIT have? Like the system always will work.
Once more, please.
How many clusters?
Clusters?
Yeah, processors does MIT have? Like will work on systems like high parallel systems. So how many will that system have?
How many processors?
Yeah.
Frankly speaking, I didn't clearly know which machine we. Okay, we will be given some information about entering some remote machine. So I don't know which remote machine will be. It depends. I don't know. If we get logins for big machine, that means there are, I suppose, I don't know, 512 processors, I suppose, or maybe twice of this number, 1,000. I don't, but of course, for our purpose, firstly, we will not allow to use the whole number of processors, of course. And for us, it will be sufficient to use, for example, 16. It will be sufficient to see or to touch or to learn how to operate with MPI, with OpenMP. It will be sufficient. So we will use, I think, not more than 16 processors. Processors and core, this is equivalent. Processor core. Okay. Login, I don't know. So, have you deal with Linux? Do you know all commands and so on? Okay. The main, okay, if you know about Linux, I think you do not know about SSH, Secure Shell, or you do know?
Yeah,
No.
Yeah, to connect to a remote machine.
Okay, that's okay. So SSH, and we have to know our login and some remote machine name. I suppose that this remote machine name
Why is it so? I think it will be named as something called Физтех-школа or something like this. It doesn't matter, so we'll see. Do you know, or okay, if you know some Linux commands, I suppose that you will familiar with some editors, because we will write programs and we have to use some editors. So you are familiar with this one. Okay, so I can show you because of course we have to once more, because our classes will be here, so you can see there are no any computers here. So do you have notebooks? You don't have. Desktop at your home, yes? Because for our classes, I always said all students have notebooks, and there will be no problem if we use this class, because computer classes now all fulfillment of all computer classes. So we will be given with this auditory, and it's a pity, of course, how to. Okay, I will think about this situation, but maybe you just have to sit near your friend and show, and maybe I don't know how to. But now we can. You can just only see. It's a pity, of course, because it will be very good if you type your first MPI program by yourself, and I ask you, okay, not ask you, I ask you, okay, to make these operations by your own hands at home, and try to type, not copy paste, but try to even once in your life type MPI functions by yourself. After that, try to launch it and see the result. Now we can consider this program very simple program, but this program, if you write it, it will be the basis of your first homework. It will be the basis. And you can just add something to this first program, a little bit here, a little bit here, and finally it will be your first homework. And I suppose it is fine. But now I can just show you something. Okay, so you can see here, red, let it be red. On my screen, this is red. This red. So red, with the red color will be new information. Some new information concerning MPI. For example, this is MPI header file. This is MPI some data type, and this is some variable of this data type, and so on. So we can add this header file, some variables of integer type and some variable status with this type, type. So I will write down this code by myself and will show you. Let it be hello world MPI CPP. Let it be like this. include. Okay.
We can also use Windows to connect to the remote server. Can you use Windows to connect to the remote server?
I think you later you will enter the remote center. Now I am in remote computer, but another one. As I understand you. So you can see, and I have to make these letters bigger. Okay, I can see, I can. Maybe like this will be more convenient. Gabriel and Daniel, are you here?
I'm here. Yes, sir, I'm here.
That's right. Very nice.
Of course.
Who knows? So you can see what I'm doing, yes?
Yes, sir, you can. Yes.
And include mpi.h. Okay. Int main. So and if, as you can see, function main have to be with its arguments. It's yes, of course, command line arguments, but it is one minute. Important because of I'm using English language rather seldom, so it is no, not of course, but not so frequently as you, I suppose. And some words, and during our discussion, some words can just flow out of my head. And so it is important because and you have to put these command line arguments always in int main function, Так. Okay. What after this? After this, you can see some. Okay, copy paste will be faster. Int I, some variable array. Okay, some array, and my rank and size. Let it be. Rank and size is the total number of processes which will work. Okay, will be working. Yes, will be working inside your program. And my rank is the number of one process. For example, if there are 5 processes at all, every process will have its number. My rank is the number of process, and these ranks
will start from 0 to size -1. So if there are 5 processes, that means these ranks will be 0, 1, 2, 3, and 4. And MPI status and some variable status. Okay, let it be like this. And every MPI program has to begin with these 3 lines: MPI init, MPI comSize, and MPI comRank. These 3 functions, this preamble of any MPI program. Before these functions, you cannot allow to. Okay, you do not allow to use any MPI functions. After these 3 lines, it's okay to use. You may use any MPI functions. Before, no. So MPI init. This is function of initialization of MPI, and you can see that arguments of this function is the arguments of what? Yes. These are the arguments of main functions, argc and argv. So when you launch your program, you set up a number of processes. This number will be inside main through these arguments, and after that, this number of processes, for example, will be inside, let's say, MPI, inside this using this function. After that, function MPI comSize writes this number of processes into the size variable, and function MPI comRank will write rank of this process into this variable. This is one issue. Let it be, let's say, like this. When I write declare these variables I, array, and so on, and launch my program using different or a lot of processes, that means all these variables will be inside these processes. For example, my program runs on process number 0, process number 2, and process number 1. This is ranks. This rank 1, this rank 2, and this rank equals to 0. Okay? If I type I here, that means this variable with the name I will be inside this process, inside this process, and inside this process. This will be not copy of this variable in every process. These are all different variables, different. They just named the same. They name this name. These names are the same, but in reality they are live, let's say like this, on different computers. This lives here on my computer. This lives on another computer, and so they are storage. They are in storage of different computers. in the memory of different computers. And array will be here, and will be here. And these arrays also they are named the same, but they are all different arrays, and so on. And for example, size will be here, size will be here, and size will be here, and my rank also. So function myCompSize will write 3 processes. So the value will be 3 in variable size. So in every process, this variable size will have the same value, 3. And PI.com_rank will write rank of the process into the variable myRank. This variable is in the process number 0. So what will be its value? 0. Okay. In this process, 2, and will be just 1. Okay. That's all. So every process contain or keep or store. Yes, every process store such variables, and in this process variable size will contain 3, variable myRank will contain 2. Different process will contain or will keep different variables. Their names the same, but in reality they are all different things, all different variables. They differ from this one, differ. Array, and this another variable in another computer will contain 3, and this myRank another variable which is another computer, personal computer for example, or another node will contain 0. Okay, if we consider 5 processes, that means it will be more variable with names size, more variable with name myRank, and so on. But every variable with the same name can contain another or other information, different information, because this process see just these variables, and this process with rank equals to 0 see just 2 inside myRank, not else. Do you have any questions? Gabriel, Daniel, do you have any questions? Do you have no?
From me. No questions.
Okay. So I'm just and finally every MPI program should finish with this function, MPI finalize. After this function, you do not allow to use any MPI functions. Okay? So, function int main that we have to return something. And what else? So, this is the simplest program, simplest MPI program. Save. And we have to do something. What it will be? Let's print. Okay. Prints my rank, for example. My rank is, and the whole size is. So let's see the rank of each process and the whole number of processes. Okay, my rank is my rank, yes, and the whole size is size. So we have to launch our program, yes. How to launch? Maybe in our machine we have to add some module, but okay, I think that I will do without any addition. So we have to consider compilation firstly. We have to compile our program. MPI CC is for C file, MPI CC compiler. If there will be CPP, C++ program, that means MPI++ or MPI CC capital. Just 2 letters capital, CC. And the default executable will be named as a.out, as you know. Okay, let's compile firstly. Compile. I have saved and compile. So, do you use which operational system do you use? Okay. Okay, Mac. Something.
I use a MacBook too.
Which? All of you?
No, I use Windows.
Windows. So for Windows, there is 2 useful programs. Terminal is a PuTTY. I don't know why is it so, but it is doesn't work now. PuTTY. And another is WinCPP. WinCPP is a file manager. When you using it, you can open your directory in the remote machine, open your programs. For example, here I can edit something with the network, because I cannot. Something with the network, I suppose, with the connection. Okay, what we will do? Something with connection. Okay, so 2 useful programs for Windows. For Mac, the terminal you can find inside Mac. It's already here. For Windows, terminal, where you can, or SSH connection. You can establish SSH connection using this program terminal. SSH connection is a putty. Huh? Windows command? It's not so convenient because here you can store or save your session, your connection with the login and the name of remote machine and so on, and make some settings more convenient. And the second program is WinSCP. WinSCP is a file manager. File manager. File manager. Something with connection. Something with the Wi-Fi, I suppose. Okay, I will try to locally, to show you locally. Something with the connection.
So can you finish the class at 13:30?
Huh?
Can you finish the class at 13:50? 1:30?
Of course.
Like, I mean every week, because we have a class right after your class.
Just equally to 30. Yes?
Yeah, 13:30.
I see. Just today.
Not just today, every week. Because we have a class at 2 o'clock. 1:50. At 1:50, so we need 20 minutes break. Because we have a 3-hour class and then there's the next 3-hour class.
Will 10 minutes sufficient for you to go to another class?
No,
or no?
that's
No?
exactly why I was asking you for 20 minutes.
20?
Yeah, if you stop at 13:30, we have at least 20 minutes. I can show you that.
And where you have to go? New? It's a little, it's near here.
Yeah,
I think that 10 minutes will be sufficient to go.
I mean, only if you're comfortable with it.
10 minutes I think will be sufficient. Why not?
We have a class at 13:50. So if we stop at 13:30, we can have a 10-minute break.
Just 40.
Okay.
Not 45, but 40.
Okay, 40 or, yeah, I was telling 30, but if you're comfortable with 40.
Okay, 40. Let it be 40. Something with the connection, but nonetheless, we'll see. Так. And. So now I'm using, of course, CMD of Windows because I launch locally. Так. So here I compile using just my environment. You cannot see this line, but I will launch my program using this line. Almost this, because my program not a.out, but
but hello world like this. Oh, much better. Yes. Okay, MPI run. This is a program to run my program. MPI, that means MPI functionality. After that, I have to put here one argument, minus NP. NP means number of processes. For example, 2 and the name of my program, hello world exec. Let it be like this. Why is it so? Why is it? MPI exec. Okay, here so it can be MPI run or MPI exec in the cluster, but here I suppose it will be just MPI exec. In my environment, in my Windows system, there will be just one MPI exec. So you can see I have written one line here. One run, just one line. But in the terminal, you can see 2 lines. What does it mean? How do you think? What do you think? Now we do not distribute anything. I just force to every process print something, and every process print 2 things, 2 variables. One variable is its rank, and another variable is the whole number of processes. That means my rank is 0 or 1 for one process, and the whole number size is 2. For example, if I run my program using 3 processes, for example, okay, 5, let it be 5. We can see 5 lines. Every process print its rank, and because every process know about its own rank, it print its own rank.
The one which finishes, why is it in a random order, 2, 1, 4, 0?
Because this is a stochastical process. I mean, when you launch, for operational system, it doesn't matter which process will print firstly. And from this point of view, it doesn't matter because they are all equivalent to each other. They are all the same. For machine, they are all the same. They have their ranks is for human only. To make human or you use each process differently from each other, from another processes. But for machine, all processes are the same entities. And for example, for computer, the order of appearance of these lines are the same, because for machine, all processes is the same. But somehow for you, they are different, and this is random process, stochastical process, and you do not know which process will print its information. It just, I don't know. Every time it will be different order. It's okay. Okay, go further, or you have another questions? So that was about compilation, but I can't show you the compilation by my hands to type this line, but I show you launching. Okay, go further. The main things of using processes is that actually they do not have any information about variables which are in
the memory of other processes. So every process, for example, this one, number 2, it cannot read any information directly from this process, from its memory. It cannot directly read because the memory is distributed, spatial distribution. The memory distributed in space, in physical space. The memory is not shared. That means it cannot read directly from the memory of this or this process. It cannot read directly. But there is another way. All processes can send some information to each other. This information is called messages. That's why message parsing interface, message between processes. And for example, this process can send via message this variable here. And using this way, this process can read this memory indirectly. Okay? So this is the process of sending and receiving messages or information. Okay, let's send some information from one process to another. To use this, to send some information, you have to one minute. Okay, we may say process number 0, please send something to process number 1. To say something to some process, for example, rank equals to 0, we have to use if statement. If my rank equals to 0, that means if rank of the process equal to 0, that means this process do something. Yes? Okay, what it do? What it can do? It fulfill the array. Each element of array equals to the index or the I. How it will be in English? Just index. No, let it be index. Okay. So this is a fulfillment of the array. After that, a process number 0 sends part of this array. This is the first. Okay, the first argument is the address from which the information will be sent. 5. The number of elements with type NPI int, integer type. 5 elements of type integer will be sent beginning from this address. To process number 0 or to process number 1 with the tag of message equals to 1. Tag means some identifier, ID of the message. And this will be, you have not asked any question about what does it mean NPI convert, because it was already here, for example here. So NPI convert is the name of communicator. Communicator is the environment where all processes have their ranks. Let it be like this. NPI convert is the main global communicator which created when you launch your program. Okay, we will not consider any other, maybe, I don't know, maybe a little bit later, but now there will be just one communicator, a global communicator, and where it is needed, it can be here and should be here. So let's see a little bit in detail. Process number 0, it has array of 10 elements, yes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And process number 0 fill with the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, 10 elements in array. What does it mean? This one, what does it mean? And percent array 5. This is the address. Address of which element? One, 2, 3, 5, 6. This one, yes? Okay. So this is address from which the sender will be. Yes? How many elements? 5. Type NPy int. NPy int equivalent to C int, to the integer. So what does it mean? It means that if we know the quantity of elements and its type, we know, or NPy know, the size of information in bytes. Yes? So number of bytes. Number of bytes. Because, for example, one integer is 4 bytes. 4 bytes consists of 4 bytes. If we send 5 elements, that means we send how many bytes? 20. If we send NPy double, how many bytes will send? 40. Yes. That's why we have to say NPy from which, how many elements, and which type. So NPy knows the point and how many bytes it has to get out memory, put this number of bytes in the network, and these numbers via network to another computer, to another process. Another computer, another process. Process number 1. It lives inside another computer. Okay? Network. Network. Now, it has also the array consisting of 10 elements. This is the middle. Let's see one thing. If my rank, okay, let it be without sending. If my rank equals to 1, without receiving, and let it be, okay, like this. Firstly, firstly, let's see what will be in the process number 0. So it fills the array, and okay, let's print the whole array in this process. Let's see. Yes, like this and like this. So you can see process number 0 prints the elements of its array 0, 1, 2, 3, 4, 5, and so on, like on the desk. Okay, let's see. I just comment and let's see. Let's print. Let process number 0 print its array. Okay, we know that the name is the same, but it is the absolutely different entity. Okay, let's see what it will be. What is this? Some information, but I suppose there's 5 elements. Okay, let it be 10 elements, the whole array. So you can see some garbage. Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 elements. 10 elements which contain garbage. Because this is the initial values of this array. You can see that in the process number 0, it is already reasonable values, because process number 0 has filled this array. But process number 0 has not filled. Yes? Okay, let's see what will be if we send some information from process number 0 to process number 1. Which part of this array process number 1 sends to process number 0 sends to process number 1? Which part? The second part. Yes? The second part of the array. Okay, the second part. Okay. And we can see that receiving function will also contain almost the same arguments. Address. What does this address mean? What does it mean if I put here just the name of the array? What is the address? Without. Yes, the very beginning. So process number 1 will write the receiving information just from the very beginning of its array. And it will write 5 elements with MPI integer type from process number 0, and this is the tag of message. So the ID or tag message has to be the same, must be the same. MPI convert is the name of communicator, and the last argument is our status variable that was declared at the very beginning. It has type MPI status. Okay, and just print all the elements of the array inside process number 1. Okay, so here we have to suppose that first 5 elements will be the 5 last elements of the array inside process number 0. 5, 6, 7, 8, 9, and what will be here? How do you think? What will be? Garbage. Some garbage. Okay. Let's see. Am I right or not? So I'm and you, we are all right. 5 elements from the very beginning and 5 elements which contain garbage. So now you can see that before sending, process number 0 has nothing inside array, but after sending, it contains 5 good elements. Okay? Okay, go further. And there are some useful information, but I think maybe further. Okay, so let's consider this slide. Because of we have to measure the speed up. Okay, to calculate speed up, we have to measure time. The time is measured a little bit specifically in MPI programs. And to measure the time, you have to use NPI WTime function. It returns some number of seconds from some since some point in the past till now. And you can use this function, for example, in the very beginning of your program and in the very end. And the difference between these two times will show you the time, rather than the running time of your program. But this is the simple way, some variable, double, begin, end, but there is some issue, a little bit question, how to measure time. Okay, let it be double here, double begin and end, yes, for example. And in the very beginning here I print MPI. As you can see, there is without argument here, but we use our variable in the left side from the equal sign. So begin, okay, I can just copy paste. Begin and here end. If you use such a functions here, what will be? How do you think? And let's say here print time of working, for example, working equals to something like this, and let it be end minus begin, yes? What will be? How do you think? If I print in the main part of my program outside any if statements. Okay, let's see. This line was printed twice because process number 0 printed and process number 1 printed, and you can see that the difference is twice. Okay, there is some difference between these two values. Here you can see 0.0014 and 0.30 and 6 and so on. So you can see some difference. What is this? Firstly, you have to, you can imagine that every process runs independently, and if I draw like this, that means every arrow means process is working. If this arrow is has more length, that means process. This is time of working, and that means this process number 1 is to working faster. Somehow, I don't know why, but process number 2 a little bit slower. And what it means? That means that if they are compute the working time, their begin and end located at different time points. Something like this, here and here, here and here. One process can run faster, a little bit somehow, another process a little bit slower, but how do you think? What is the time of running of this program, running time? You can see that one time greater than another. Which time is the running time? Will be the running time? Greater one, of course, greater one. Okay, greater one, but how to make it better, make our program better to get this better to greater time? To do this, we have to add some function. Here, for example, MPI barrier, MPI com world. Let's see what will be. You can see that these times are comparable. But not always. So we can see the difference as it was earlier. Now it's comparable. Okay, let's add the same MPI barrier before end here. You can see.
So what does it mean?
1 minute. So you can see the times is already almost the same. The difference is much less. So what does it mean? Every operation like MPI send or MPI receive, this operation is called as point-to-point operation. Point-to-point. That means this operation deals with just two processes, just two, one and another. When process number 0 sends some information to process number 1, that means only two processes communicate with each other. But there are another or other operations which include the whole pool of processes, and these functions are called collective operations. We will consider this operation a little bit earlier, but to measure the time, one operation is needed. What does it mean? So MPI barrier, if there is an MPI barrier yes, that means if this first process which execute this operation, it will wait till other processes will execute the same operation. And after that, when all the processes execute this MPI bearer function, they all simultaneously will start to do something else. That means if we write barrier and after that double time, that means we fix this point for all processes simultaneously. And so when you use end and fix the endpoint, you have seen if we fix just the beginning, one time there is good difference between times, another not, because they start simultaneously. We have fixed one point, but we have not fixed the another point, and because of different speed of processes, there is difference between times. Now, when we fix this and this one, there is, of course, it will be some difference because of non-ideality of our computer system, operational system, and so on. But this difference is rather small, and I suppose we cannot make this difference smaller, and it will be the accuracy of our management. It will be rather good. Okay, so this is one point. Okay, already 37 and 3 minutes. Yes, till 40. Okay, let's. I can listen. Okay, what about your questions? Okay, 3 minutes for questions, and we will continue our discussion next week. So now you can ask any question if you have, of course.
Sir, I have a question.
Yes.
Can you please pose the syllabus of this semester, if possible?
I didn't catch. I'm sorry.
Я могу сказать по-русски, если...
Of course. Давайте.
А вы можете послать все топики, что мы будем проходить в этом семестре?
No, I can't send you, of course. I will send you all of the files, presentations, using Telegram groups, because I suppose I have added to this group, yes? But not at the same time all the information.
But like
step by step. Now I will send you today presentation. I will send the today's presentation to presentation, and yes, I will send you.
Perfect. Thank you, sir. Thank you, sir. Thank you.
Is there like any literature that we can check, like support material?
Now, what do you mean about support material?
No, I mean like something to read by yourself if we want to.
Okay. It's a question. It's a good question, because I know just the information just in Russian, and what about English? It's hard to me to say some literature in English, but I suppose I think I will try to find something in English.
But if you have some literature in Russian, maybe you can send the names on the Telegram group, and maybe, I mean, I can check it, because I understand little Russian, maybe I can understand something. It will also be helpful, even if it's in only Russian.
Some people speak Russian in the group, like, for example, I know Russian as well, so I think Russian literature is going to be great.
Okay. I can send the literature in Russian, and but there is another question. There are, for example, authors from Russia and authors from English-speaking countries, for example. If the literature or the book was written in Russian, that means two ways. Firstly, it was Russian author, and second way is the translation from English. So maybe if I think I know some book, one book from English speaking author, and it was translation, and maybe you can find in English, this book in English. I suppose you can find this. But also I can give you the literature in Russian, of course.